Let's get started. So today we're going to be talking about some Markov chains. It's the first lecture in the section on so graphs. Right, so here's the schedule. We're getting towards the end of the semester, so for better or worse. And so the last 4 lectures will be on so analyzing graphs as they come up, and from social network analysis, and so that'll probably be the main kind of target days that we'll use for applications of these things. And so there'll be one homework assignment associated with this section. It'll be due, what do I say? I think this is reading day. I think it's okay if you have an objection with this due date, please. But please let me know. But I think this seems reasonable. I want to keep it on a Wednesday, just for you're used to turning stuff in on Wednesdays. Okay, and I'll have that out probably on so this Wednesday. It should be, the actual stuff I ask you to do should be kind of similar to onto the last sort of assignments. I would say probably, I think probably even simpler. And I think I have a bonus question worth like 5 points that shouldn't be too hard. So if you're really desperate to make up some points, there's some chance to do it. A few points here. Okay. And so the other thing, hopefully on your mind, is that the final report is going to be due in a week. Okay. Good. Yeah. So not on April 1st. Okay. Okay. So what do you want in the final report? Okay, so just to kind of talk through this a little bit. This is worth like a quarter of your grade, the final report itself, roughly. So try and make sure you do a good job on it. And I will kind of, like, most of the project has been there have been milestones that if you reach these milestones, if you do what I ask you to do, you can get full credit here. On the final report, I will be slightly subjective about things. There are some groups who are just going to go above and beyond and not just meet what I asked you to do, but do a lot more work, and I'm going to give those groups more points. But I'm not going to give anyone more than 50 points, right? We don't have an A+ here, so I can't give you kind of extra credit. So that if you just do the average, you'll get like like 40 to 45 points. Okay. But that should still be enough for an A, so you should be fine. So okay, and then the size of the report is going to be at most 4 pages per student in the group. So if you have 2 people in your group, that's 8 pages. If you have 3, that's 12. If you're one of the few single people groups, that's only 4 pages. Okay, that's all I'm going to read. Right? You can have an appendix. You need to mark it as an appendix. I can't read everything if you all turn in 100-page reports, right?
Yeah. The graphs that we include
the graph should be in the first.
Count toward the 4 pages.
Yes, okay. Yes, they should. If you want me to look at them. If you don't want me to look at them, you can put them in the appendix. Okay. If you describe them, if you think they're worth making, put them in the first 8 or 12 pages. Okay. If you put it, I say that explicitly somewhere in here as well. Okay. So please. And don't use like super small font or super small margins, right? It should be kind of 11-point font and like an inch margins. You can use less space. That's fine. If you can convey the same information in fewer pages, I'll be super happy. That's probably you did a good job of writing. Okay. One reason for this, I know you guys have done a lot of work and you have lots of cool stuff to tell me, but in life, you're going to have a manager or boss, and they're not going to read thousands and thousands of pages of documents, they want a nice, concise summary, and that's what I'm going to read as well. Okay? So, so what should be in these 8 to 12 pages? So first thing, make sure it has a title. You're going to have the same title on your poster. Okay, so choose your title now. It should not be like, it should not be called My Final Report, right? It should be what you're actually, actually doing for the project. Okay, and it should have your names up there, right? Have this be something proud of. You're going to have this document. You can link to it off of like a page you have to when you're applying for jobs. Have something to be proud of. Put your name on there. Right? And then it should have kind of the basic problem and motivation, and kind of, it should be telling a story, right? So it should have a single narrative to it. Even if you have multiple people in the group, and they're working on somewhat different pieces of the project, and this is totally fine, the report should be a single narrative. You're going to set up the problem. It's going to have some motivation, some reason why you're working on this problem. Right? Why the problem is interesting, and then tell me what you did, right? What sort of data you worked with. This could be from your data collection report and so forth. What was the key idea? What was interesting about this, right? If I just said, okay, I took this data, I ran these algorithms, and here's what the output was, I'm done. That's not a very interesting report. I want some key idea. I took this, I modified it this way. I didn't know which of these algorithms would work best, so I tried both of these algorithms, and here's how I compared them. Right? So bring something interesting, highlight the key idea. My favorite part about this, about teaching this project part is reading these and learning cool stuff from all the projects that you do, right? Some of the reason I think I'm gotten fairly knowledgeable in this area is because I read a ton of projects every year where students go and try stuff, and they tell me what they did, right? So so please tell me something interesting that you did. If I learn something, I'm going to be really happy, and you'll get a higher grade. Okay? So good. So and so kind of tell it in a narrative, right? So motivation and then what you did. If different people in the group did different parts of it, then you can kind of have subsections with them, but they should fit together in one coherent story. It could be there's one data set you want to learn about, and you have two ways you looked at it. That's okay, right? That's fine. That can be the same story, but don't have them be kind of completely disjoint. Okay? And then kind of have something that explains what you did and what you learned, right? So, and try and draw a conclusion. So you tried different approaches. One of them worked better than the other one. Why do you believe that, right? Is there runtime? Is it that you could show there was small error? Maybe there are cool examples you're going to pull out of your data set. Sometimes you can actually quantify it using cross-validation. Other times you can't. Can you show pictures? This one visually looks better. That's fine, right? I want some sort of quantification of this worked or this didn't work. And look, if you had an interesting data set, it seemed reasonable, you tried techniques the right way, and your conclusion is that things didn't work, nothing interesting, there's not the structure there that you thought was there, that's okay. You can say that, you can explain that. Some of the interesting things I've learned is that for this type of data set, this technique does not work. Right? That's good to know. It's better than claiming something worked when it's not supported by the data. If you claim something works when it's not supported by the data, or you use, like you're doing clustering where the distance function you're using just does not make conceptual sense, and you're claiming there are really good clusters when I don't believe it, then you might not get as good of a score. Okay, but if you tried something that was reasonable and it still doesn't work, I'm not going to take points off for that. Okay? Okay, so also this is part of the class where I've heard other professors say that students complain about having to do writing and presentations and stuff like that. Because you're computer science students, you know, this is really important. You're going to be kind of doing analysis and writing code for your career, and if you just do that, you're not going to get recognition for what you did. Okay, if you can communicate that to either investors or your boss or people in the marketing department, you're going to get a lot more recognition for that. You're going to get credit. It's going to help your career. Take the time to try and do a good job on this, right? Do it, then put it down, read it again, say, did this really convey what was going on? Did I make this exciting? Take the time to try and do that. You really learn by practicing doing it, and you're your own best. If you can learn to be your own best editor, then that's going to help you a lot. If not, you have project partners. Have them say, did this convey this the right way? Is this exciting? Work together on doing this. Okay, it's totally worth your while to spend a little bit of time doing this. Okay, there'll be a poster presentation. I'll talk more about that afterwards, but be prepared. This is one of the reasons why the final report is due a little bit earlier than the complete end of the semester, because you're going to have to do this poster presentation and outline. So the report's due next week, Monday, but a poster outline's going to be due next week, Wednesday. Okay, that's outlined. The final poster will be due, I guess it turns out will be due on the day of the interim test in the morning. The department will print these for you. This is the last year we'll get the department, I think, to be able to print them all for you. But they have to print 50 posters for all of your groups, so we need to get them in by Monday morning so they can start printing them. So we're confident they'll be ready by Thursday. Okay, so you'll turn in a poster outline, and I'll talk more. I'll bring in the example posters again, and then turn this in, and we'll try and give you feedback. And then when it's ready, we'll take them and we'll send them to be printed. I updated a little bit this part of the document, so we're changing a little bit this year in how we're sending them off to be printed. So you don't end up sending email, but we'll do like approval through Canvas, and then we'll pull the PDF out of there once we both agree that it's the final version. Okay, but look to this and you can start thinking about the posters, and you can add more content to the posters and your report if you want to, but your project will be graded on the final report. All right, so any questions about this? Yeah?
Are the posters going to be in color?
Yeah, the poster will be printed in color. There's notes on there about, it's great if you can try and use a white background. It's just easier on the printer. If you have a great reason where you're doing some really cool creative stuff and you think it really needs to have this cool stuff in the background, that's fine. But don't just put like it's a purple background just for the sake of it being purple. Okay. So it's good to have highlights and stuff like that, but just kind of superfluous kind of color is advised against, just to make it easier on the department's printer. Okay, great. Okay, so let's talk about Markov chains. This will be a lecture where I mainly don't get into actual kind of analysis techniques. I view this as really foundational to understanding the techniques like PageRank, which we're going to be talking about on Wednesday. PageRank is kind of the algorithm behind the it's like the search engine for Google, and it's kind of has been extremely influential. And to understand it, really understand it, you should understand some Markov chains. And okay, so part of this lecture will be some some definitions, and so to try and liven it up about a bit. So Markov chains are kind of some life lessons you can learn through this analysis. So which we'll see in the context of the mathematics here. So so first one is only your current position so matters going forward, and you shouldn't worry about the past. Okay. This second one is you only need to worry about one step at a time. So and you'll get there eventually, or maybe you won't. And the third one is that in the limit, everyone has perfect karma. Okay, so we'll see these now. We'll come back to them later in the lecture, and maybe they'll make sense, maybe not. So we're going to be talking about graphs, and so kind of the canonical example used in data mining community often is where you have like a social network, and so you have each kind of node in the graph, A, B, C, D, and so on, like you saw with spectral clustering, is kind of like a user in the social network, say on Facebook, and an edge as if one person is following the other person. Okay, so we can talk about these directed edges now, where you could have A is following B, but B is not following A. And so this matters some in the context of like the social network. In a lot of the large-scale analysis, it often does not matter too much. If you just kind of add the edge going back the other way, for a lot of contexts like spectral clustering, it doesn't change stuff too much usually in the result. And so there's some rationale behind this I'm not going to go into. So if the direction confuses you, you can probably ignore it. It's largely okay. But in Markov chains and in PageRank, the direction is going to matter. So and then you can write down the vertices of lists of edges like in spectral clustering, and we'll be working with this adjacency matrix, right? Where I have A is connected to B. If then there's a 1. If B is not connected to C, there's a 0 here, and we'll treat this as just as a matrix. If there are n vertices and it's an n by n matrix, 0s and 1s. Okay, we've seen this before. It's been a few months ago. You've hopefully seen graphs in other courses as well. Okay, so with the Markov chain, the Markov chain is going to be defined by 3 objects here, V, P, and Q. Okay, V is going to be the node set, the vertices of the graph. P is going to be a probability transition matrix. And this is essentially, basically, this guy is being defined by the edges. Is being defined by the edges in the graph. Okay, so I had a graph. I have the vertices and the edges. Now I have the vertices and the probability transition matrix. And so it's going to look like this. And so what I've done is I've taken the adjacency matrix, and I've looked at every row, and I've made it row normalized. Okay? And so I've not made these into unit vectors. I've done that basically P row I. So this is the ith row is going to be AI divided by, and that's the ith row of A. Remember, A was this adjacency matrix here, right? And so this would be A3, right? So it's going to be A this, but normalized and an L1 so normalization. Okay, so that means I'm dividing by the 1 norm, and instead of being a unit vector, which means that the Euclidean length was 1, I'm saying that the L1 length, the Manhattan length, is going to be 1 now. And that means that, so the property is going to be that it'll have the property that each Pij is going to be greater or equal than 0. And the sum over j equals 1 to n of pij is going to be equal to exactly 1. So that means this is capturing a probability distribution. Okay, it's the right way to think about it. Okay, so a different way of normalizing the adjacency matrix. That's the probability transition matrix, and we'll see how this is used in a second. The third element is Q, so this initial state. Okay, so we will sometimes not need the initial state in the definition, but to kind of give you a full sense, let's start with this, and this will be kind of again a vector representing a probability distribution. So these will be in this probability space again. So again, this means I'm going to have the property that each qi is going to be greater or equal than 0. Some of them are 0, some of them could be something greater, and that the sum over I equals 1 to n of qi is going to be equal to exactly 1 again, right? So these are again a probability distribution. Think of this as some sort of initial state. And there are two ways to think about this. Two ways these exist, and I've given two examples here. The first way is that it's going to be all zeros except for one non-zero, and this basically means that I'm at B. So I'm exactly at this node right here. So I'm exactly at this B node. With probability 1, I'm at node B. Probability 0, I'm everywhere else. So I have to be at 1. Okay, so my initial state, I'm at exactly one of these nodes in the graph. And then the other example here, right, so if I look at this example instead, now I'm saying I have a probability distribution where I could be at node A, node D, or node F, right? So 10% the time I'm at A, 30% at D, and 60% at F, right? So I say I don't know exactly where I am, but I put some probability distribution describing where I might be. Like I'm in like a quantum state or something like that, where I'm kind of between these different roles. Okay, so it could be, these are think of this like, it's like a map, right? Where are the places I'm at during the day? 60% of the time I'm at home, 30% of the time I'm going to be at work, and 10% of the time I'm going to be at the restaurant or something like that, right? So that's an initial distribution of where I might be starting out. Okay. Okay, so these are the three initial parts, the kind of the node set, the possible places of where you could go, the probability transition matrix, which is the normalized row normalized adjacency matrix, and then the initial state, which tells you kind of a distribution of where you're starting out. Okay, and so how you do this? The interesting thing about this Markov chain is that you take a state and you apply the probability transition matrix, and it changes so where you are. The edges tell you the connectivity. If I'm at work F, I can only go to H, G, or E. I can't go directly to, or if I'm at home, I can't go directly to work. I have to drive in my car first, something like that, right? Or I have to go someplace to the subway station, the bus station before I go there, right? So you have to have these intermediate states, and the probability transition matrix tells you where I'm going, right? So this row tells me I'm in state A, and then I will, these are the states I might go to, right? So I might go to B, C, or D. those are the states I could go to, and that's based on the connectivity. If I'm an A, there are edges to B, C, and D. Those are my possible states I can go to. Okay, and it's a 1/3 probability of going to all of them, unless I could change these probabilities, but if I just have a graph, I'll make it equally likely for all of them. Okay, so what happens if I start in state B now, right? This was the initial state here. So if I start in this initial state and I'm at B, right? Then with 1/2 probability, there are only 2 choices, right? So now I'm looking at this edge, this column here. Oh, I just realized I've been saying row normalized when I should have been saying column normalized. Okay. Okay. Good. Okay. 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 Very sorry about that. I get those confused sometimes. Okay, so we've been column normalizing and talking about columns. Okay, so I look at column associated with B, and I'm saying half the time I'm going to A, half the time I'm going to D. Okay, column normalized here. Okay, so and so I can reflect that in this update of my state vector Q. I go from Q to Q1. Half the time I'm at A, half the time I'm at D. And then I can keep doing this, right? I can apply this probability transition matrix again. After 2 steps, now this gets distributed further. From A, right, I can go to B, C, and D. I can go back to B. I can go to C or D. And from state D, I can go to, let's see, from state D, I can go to A, B, or C. Right, and so it's higher. I'm more likely to be at states B and C because those have 2 ways to get there in 2 steps. Where at A and D only have 1 way to get there. And after 2 steps, if I start in state B, I cannot get to any of these states. I just can't reach there in 2 steps. Right, so if I look back at the graph, if I'm at the pink node D, I just can't get to state E or even state H in 2 steps. There's no way to get there. Right? Okay, and then I can take 3 steps, right? And so I can, and then this distributes further. There's some chance of getting out to E now, right? I could, if I make 1 step further away in 3 steps, I might make it out to E, but I have to kind of do everything right. Okay, and so I wrote out there multiple ways of doing this. It's all linear algebra, right? So Q1 is Q times P. Right? But Q2 I can get as either Q times P squared, or Q times P, or Q1, which is the output of the above, times P. Right? I can write P times Q is exactly Q1 and plug it in here. Right? These are all different ways of thinking about this. So I could actually, you could write down a matrix which is P squared, which is the matrix P times the matrix P again, and it will give me a probability transition of where I can go in 2 steps at once. I can pre-compute 2 steps ahead or 3 steps ahead if I want to see how to get to Q3 directly from any initial state Q. Okay? So linear algebraically, these are all the same. Computationally, they're going to be different, and we'll talk more about these differences.
And the P matrix is always squared. Right?
Yeah, it should always be squared. Should have n states from any state, the transition of getting to the same n states.
Which means it's invertible, which means it's full rank, or not necessarily.
Not necessarily. So we'll talk about these things. Yeah. Okay. So this kind of tells me how you walk around a graph, right? If I have this, so the probability transition matrix is defining this kind of random walk on the graph, right? And this kind of is a mathematical way of kind of analyzing this random walk process. And this tells you, will end up telling you a lot about the structure of the graph in kind of ways which I think are kind of interesting and non-trivial. Okay? And so in the limit, right, we'll talk about what I mean by in the limit and when I can say in the limit. But in the limit, I can think of doing this to the power n, right? For a mini initial state Q, I can do p to the power n, or I can do q times p. I can do that times p n times, and I'm going to get to, say, qn, right? So we can think about this. The nth state is I'm doing this for n steps. Okay. So I want to think about this as n goes to infinity. So I want to think about, say, as n goes to infinity, then I kind of don't worry so much about how long is one time step, what does that mean? I just say, you know, if I randomly walk around long enough, what's going to happen? What are things going to look like? Okay? In order to do this, I need some conditions. Otherwise, it's not defined properly. Okay? I want to talk about the limiting effect here, and we'll see some cool stuff about that. But I can't always, there's not always a limit. There's some mathematical oddities that can prevent it from having like some limiting state I can analyze. Okay, so so we've reached the first life lesson here. So only your current position matters going forward. So don't worry about the past. Okay, so what I'm doing here, I can analyze this by only looking at my current state Q2 and making a step to get to Q3. Right? I can look at this one step at a time here, and that's how we're going to kind of worry about this. It doesn't matter where I was when I got to Q2, how I got there. I just need to know this state distribution, and that'll tell me about the next state. Okay, so these are called Markov chains. Okay, and so this naming comes from Markov. So there's this it's like there's these things called these Markov processes, which are analyzing kind of states over time or other things that happen over time. And these are certain ones that keep track of current information about the current state at that time. Think of like these finite state machines you may have seen elsewhere. And Markov processes are ones that only look at the current state in order to know what's going to happen next. They don't need to know historically what happened, how to get there, and so that's where this name comes from. Okay, so it's if you need information about the past, you somehow need to store that in the current state if you're going to use these sort of ideas. Okay, so I want to pause before I start talking about kind of the analysis of this. Is that there are two kind of perspectives on these Markov chains. Okay, there are two main perspectives, and probably probably you guys may have heard of Markov chains in previous courses. You know, it's also not all of you necessarily, but you've probably heard of them. But usually you've heard of them in only one of two ways. Okay, and these correspond with these two example ways of thinking about these like initial states. One way is thinking about them as a random walk. Okay, and so in this way of thinking about it, each state Q is at exactly one location. Okay, so every time if I'm taking a random walk around the graph, I'm at state A, I jump, I'm at state B, I jump, I'm at state C, and I'm always at one position. And what this will tell me is that I don't necessarily know where I'm going to go, and I'm saying that, I'm saying in the future, after I take 3 steps, where will my one position be? Okay, and there are ways of kind of computationally learning this by actually taking these random walks where you send kind of a, like you're actually, if you have like one of these finite state machines, that's like an execution of a program is one way you may have learned about this. you can take a random walk in a graph by actually keeping a state at each node and making a decision and looking where where this one kind of state is going and keeping track of that. Okay, and we're going to come back to this definition. The other way to think about it is a probability distribution, on the random walk. Okay, so this is where each so like each QI, is in this space of probability distributions, and I'm keeping track of, I can start in one state, but I'm not actually in one state at any given step forward. I'm keeping track of a distribution of where my states might be. Okay, and so I'm not actually sending kind of like a little game piece that's in one state, then the next piece in the next state. I'm actually just pushing the probability forward, right? So this is kind of it keeps track of the probability syllable in there, probability of the random walk. So it's instead of actually simulating it, I'm actually going to kind of just say, let's pretend I would, if I were to simulate it, then what are the distribution of what could happen? Okay, and I think the way I described it kind of previously, it was more towards leaning this view of it, right? There was this, I have these different values of Q1, Q2, and Q3, and I have this probability distribution, which is kind of distributing and moving around as I'm going forward. Okay, whereas this random walk perspective might be more consistent with kind of a finite state machine view of the world, and so it turns out in like Bayesian statistics, the random walk view of the world is actually kind of the only thing you can compute. Where you can think of this, instead of V being a finite state, set of finite states, if it has infinite states, then I don't know necessarily how to do this, but I can do the first case. I can do a random walk on an infinite state space, and that will still be informative. Okay, and so both these methods, these views of it are useful, but they're kind of a little bit different from each other. Okay, so we're going to talk about this view for a while, and then at the end of the lecture, we'll come back to the random walk view of it, and we'll see how to use that in some cases. All right. Okay, so what I want to describe next, I want to say in the limit, right? As this Markov chain goes to kind of as I take more and more steps, but in order to say in the limit, I need a condition. So it's I need that this Markov chain is what's called ergodic. Okay, so this is some term. I don't know where this term comes from. And so we want, if the Markov chain is going to be ergodic, it's going to have a limit. And so in order to describe what it means to be ergodic, it's easier to describe what Markov chains which are not ergodic, what properties those have. There are 3 properties that Markov chains which are not ergodic have, and we're going to go through those examples. They can't have cycles, they can't have these transient states, and they can't be unconnected. So let's go through these examples. So the first example is it can't have cycles in it. And so an example here is that this simple one, I have A and B, and basically A can only transition to B, and B can only transition to A. So that means that if I start at A in every kind of even numbered step, I'm back at A. At step 0, I've started A, and at step 2, I must be back at A. Right? And all the odd number steps, I have to be at B. Right? Or in this example here, there's A, B, and C. Okay, and what's happening is A always transitions to C, C always transitions to B, and B always transitions to A, and now I have a length 3 cycle. So if I start in C, after every 3 steps, I'm always going to be back at C. Okay, so if, right, and then you can have something more complicated here. In this example, let's see, I'm going to have, think about it as A, B, C, D, and F on this side, and B, C, D, and E down here. Okay, and what can happen is A can transition to A, B, C, or E. F can do the same. Okay, but these guys can only transition back up to A or F. Right, it's getting kind of messy. If I draw the graph, right, it should be clear in the matrix here. And this is a common example of what's called a bipartite graph. Okay, so the graph has the vertices are in 2 sets, A and F, and B, C, D, and E. And within each set, they don't connect to each other. They can only hop to the other set. So that means that it has to have a cycle. It can only, at all the even steps, it's A or F, and all the odd steps, it's these. If I start over here, then after 2 steps, I'm always back to one of these states.
And this has to be directional?
Yeah. Well, all the edges here, I have a mirror edge, right? But the probabilities are not symmetric because there are 4 states down here. So from A, I have 1/4 probability going back up. But from B, I only have 2 options. I can only go to A or F. So the probabilities aren't symmetric, but the graph is symmetric.
Yeah, like the question is, can you combine the edge, go from E to A and from E to B1? Actually,
Yeah, if I started with an undirected graph, I would, if this was the adjacency matrix and I do column normalization, this is what I get. Right? So, but this notion of these bipartite graphs usually does not, usually it's discussed without being directional. So the concept is not tied to being directional. I've added directions when I have probabilities here because I column normalize based on the columns, but the original graph, it didn't need to be directional. Yeah, so this is still cyclic. So this still counts as cyclic. Anytime I have these cycles, if I have even a single edge which goes from D to E, then it's no longer cyclic. I can break the cycle, right? So I can break the wheel, right? For your, we'll see if that happens this season for you Game of Thrones fans. Who thinks the wheel will be broken? Who thinks it won't be broken? And who has no idea what I'm talking about? So who watches Game of Thrones? Okay. Who watching but doesn't know what I'm talking about? You haven't been paying enough attention. Okay, so
is it like the families who are ruling?
So Daenerys keeps talking about breaking the wheel, or she used to in earlier seasons, but talk about breaking the wheel of this kind of, it's this like the powerful control and so forth. And, so.
I'm thinking the White Walkers are going to win.
Yeah, well, that would probably break the wheel. Yeah. See, they're all historical. They're supposed to be historical records of this. So I don't know who would be writing the histories if the White Walkers won. So I'm not too worried, but who knows? Who knows? So, okay, good. So the first case, if it's going to have cycles in it, where it can get into cycles of like 2 or 3 or 4, something like that, and there's no way to get out of it, then it's not going to be ergodic, and I can't talk about the limiting distribution, at least not in the way I want to. Okay, maybe there are weird conditional ways, but it gets a lot messier. So we don't want cycles in the graph. Okay, I can have small cycles, but as long as there's some way to break them, I'm okay. The second approach that I can have is these absorbing and these transient states. Okay, so the first example here, I have A and I have B, and what happens is if I'm in A, half the time I'm coming back to A, and half the time I'm coming to B. But if I'm in B, I'm staying in B. I've got a self cycle. That's fine. I can stay in A, B if I want to. And so what happens is if I start in A, half the time I'll stay there. But if I ever go to B, I can't ever come back. Right? So B here is like the Hotel California. Right? Once you okay. So once you go there, so you can't ever leave. Right? So. So either I'm horrible today, or maybe I'm on fire. It's up to you to decide. So. Okay, so in the second example, here we have A, B, and let me keep it on this side. We have A, B, and C. We have a triple example. Let's see. A will always go to B. B will always go back to A, and C will always go to B. Okay? So A and B are fine. They can go back and forth, and they can go and do their business. But if I'm in C, I leave it immediately, and I don't ever come back. Okay? So this is also bad. Even though A and B will have some properties going on, there'll be some stuff there'll be. Once I'm in C, I leave C. I have no more information about that. Okay, and then here I've got a more kind of complex example. Now I have A and B, and I have C and D and E and F. Okay, and so what happens is once I'm in this part, I can equally mix around, right? All these edges can go back and forth. And A and B can go back and forth to each other. So from A, 1/2 the time, and these can also stay with themselves. Okay, but if I'm in A half the time, I'm going to stay in A. Half the time, I'm going to go to B. If I'm in B half the time, I'm going to go back to A. And 49 out of 100 times, I'm going to go to B. But 1 out of 100 times, I'm going to leak out to C. Okay? So this is almost okay, right? A and B are mixing and doing some stuff. C, D, E, and F are mixing and doing their stuff. But sometimes I leak from B to C, and once I do that, I don't ever come back. I slowly, very slowly leak out. Okay?
So how does this even make sense? You have fewer edges and then suddenly you have this probability 49 out of 100. Is this like the not equal weight? Some edges
yeah, so the way, I just don't need to have equal weight.
Probably imagine them as a road. One is a very wide road, right? The other one's very narrow.
Yep. So think you have water in 2 containers, right? And you're shaking up. I have the AB container and the CDEF container, and I'm shaking them up, and they're moving amongst themselves. But there's a slow leak. It's dripping from like inside of AB out into a bigger thing, right? So it's slowly dripping out. Okay. You know, this is more of a continuous thing. Think of there are pipes, and the pipe is dripping when it drips out of this nice contained system, and maybe this is oil slowly dripping out into the river. Eventually, all the oil drips out. Okay. Right. So you know, I guess I didn't define these. These would be called. These are A and B. These would be called the transient states, because I'm in there, but I'm not really committed to being there. I'm kind of just moving through, and these would be the absorbing because once I get there, I'm stuck in there, I'm being absorbed, right? So if it has these absorbing and transient states, there's also kind of issues with the limit. Maybe I know in the limit it will always be here, so maybe in this case I can kind of analyze it. But there are other things where you could have two kind of essentially disconnected absorbing states, or kind of depends on some initial conditions that it will have some weird stuff will happen. Okay, so we'd rather not have these absorbing and transient states, and if it has these, it's not going to be organic. Okay, and then the third type is going to be fairly simple. These are not connected examples, and this is A with probability 1 goes to A, and B with probability 1 stays in B. Right? I can also have where I have A and B and C, right? And so A goes to B, B goes to A, and C stays to itself. A and B is not connected to C, right? And then this is a more convoluted example. A and B stay with themselves. They have self loops. They're connected to each other. And then I have, what, C, D, and E, which are, let's see, C has a self loop and goes to D or E. D only goes to one of these, and E is a self loop or goes to D or C, and then F is all by itself, right? So this is not connected. Okay, so this, this is also not as interesting, okay? If I do have an unconnected graph, one thing I could do is I could break it into the multiple connected components, and run some analysis on each of the connected component. Just look at the submatrix associated with here. Okay, right? So maybe there are two interesting submatrices. I can run analysis on both of them. Although usually when this happens, it's because there's these dangling things that don't connect anything. This is true in random graph theory. This is true in large instances of social networks. Typically, if there's something not connected, it's some small piece. And either I can just throw those away and analyze everything else, maybe do some local analysis on those, or we'll see another approach within the context of PageRank where I basically do something random. Okay. So these are kind of necessary to define ergodic. It's ergodic if it's not cyclic, not transient, has no transient states, and is connected. Right? So ergodic means so not cyclic, no transient, and it's connected. Okay, so that means it's ergodic. From now on, for the rest of the lecture today, we're going to assume it's going to be ergodic. When the context of PageRank, we're going to need to make sure our graph is ergodic. We're going to do modeling. So we're going to start with some data in some way, and we need to turn it into a graph, and we want to make sure that the graph is going to be ergodic, so it can't have any of these kind of properties. So we'll want to model things that have these properties so we can analyze them. Okay. So now I'm going to assume it's going to be ergodic, and I can talk about this limiting state. What does this P to the N matrix look like as N goes to infinity? Right? I'm going to call that P star. Okay? I took N large enough. In practice, 50 might be enough in some settings. In others, it might be thousands. It's going to get pretty close. And then I can take any initial state, Q, right? And I can multiply it by P star, and that's the effect of taking an infinite number of steps. And I'm going to result in Q star. And this Q star will be pretty interesting. This is the converged to state. It's in general not going to be uniform. Right? So in general, this is going to be not uniform. right? So that means not going to be Q star equals 1 over n, 1 over n, 1 over n, okay? So like if you didn't know any better, you hadn't thought about this before, you're like, okay, if I randomly walk around the graph, and maybe I start with an adjacency matrix so I can walk, every place I can walk to, I can walk back the other way. This is going to kind of ensure that it's going to not have transient states, if that's the case. If the initial graph is connected, that's okay. And this will actually prevent against cycles too. So even if I start with any adjacency matrix of a connected graph, it's in general not going to wind up so it's uniform. It's going to wind up with something else. Okay? And so I can study what this quantity is. And I'll show you some examples, an example of the stuff soon. Okay, so there's some cool stuff about this. So one is, all right, so now life lesson number 2, you just need to worry about one step at a time and you'll get there eventually, or so you won't say if not ergodic, right? You can just look at what's going to happen in the limit and just one step at a time, right? So I just need to worry about this kind of one-step analysis and see where this goes. All right. So one other kind of there are lots of like really cool properties about this. One is called this. One property is called this delicate balance. And one way of seeing this is that if I start, okay, so I have this property that if I'm at Q star, if I'm at this converged to state, my probability distribution, and I multiply it by the transition matrix just once, it's going to stay in the same state, right? I'm already converged to, so taking one more step, the distribution is not going to change. Okay, and so that means also if I take any initial state Q, I multiply by P star, and I multiply by P again, I'm going to still be in state Q star. Okay, so this implies, well, it almost implies, but the intuition, it meshes with an intuition that if Q is kind of close to Q star, then then it kind of needs fewer steps to converge. So needs fewer steps. Okay, so if I'm already at pretty close to the right converged distribution, then I can only take after a few steps, I'm going to be in the right distribution. I'm in the maintain the probability distribution view of the world, right? So if I have if I'm doing an optimization, think of this like gradient descent, if you've seen that, and I'm having if I have a warm start, so I'm close to the right position, then I don't need as many steps in order to get there. Okay, and if I'm already at the right position, then I'm not going to move. Okay, and so one thing that happens when I'm in this converged to state is what's called the delicate balance, and that means that the probability that given that the probability I'm in state I at the converged to state multiplied by the transition from moving from I to J is equivalent to the probability of being in state J times the probability I'm going from J to I. Okay, so I'm going to have state I, state J, okay, and I'm going to have some probability of going from one to the other, and these aren't necessarily the same from J to I. So these are not necessarily equal probabilities of moving from one to the other. One might be 1/2, one might be 1/3, and there's going to be lots of other stuff coming off this graph, right? Which is, it's not going to, and that's going to affect what the converged to state is, but I'm going to have this property, which means that the ratio of Q star I divided by Q star J is going to be equal to the ratio of Pji over Pij, right? So that means if this way is going to be equal to 1/4, and this way is going to be equal to 1/2, right? Then it means that the converged to state of I, right, is going to have to be twice the value here, because I know the ratio of these two things. I can often talk in ratio between quantities, but often not. The actual values are going to be harder to come from, but the ratios will be interesting. Okay, so these are some cool properties that come of among this converged to state. This one's called the delicate balance. Okay. Oh, yep. And this means that in like lesson number 3, in the limit, everyone is going to have perfect karma, right? So if I'm more likely to give something from I to j, then it's going to come back, right? That's the ratio. It's going to come back at the rate I'm giving. Given the amount of karma I have to dole out, the rate I give it is going to be kind of it's going to balance out. So that means that if you're at this converged to state, let's say I'm at I, and I can look at Pij, and I know that this is going to be in return that I'm going to send out some of my karma or my state out this way, but this is also going to happen with these other states as well. Okay, these probabilities are going to come back in the other thing. Okay, and if there's, yeah, and this, I think this is only defined if they actually have a non-zero value in between them. Otherwise, this might not be defined. So, okay. All right. I also have. So one of the other kind of important things here is that I want to calculating Q star, right? So I want to calculate Q star, and we'll see in the PageRank that this is going to be a useful quantity to look at. And we've kind of I've kind of told you. I think I've told you 2 ways so far, or 3 ways so far. You can 2 or 3 ways you can compute this, right? So the first way of getting to Q star is going to be for I equals 1 to some big T. I'm going to do Q. I'm just going to update P times Q, right? I'm just going to run this inside of a for loop. I'll do this T steps, right? And so if I do this long enough, it's going to probably converge or come close to converging. This is basically the power method. So if you've seen, say, if you've taken the foundation of data analysis class, you'll see this looks like the power method, and so hopefully your wheels are spinning what's going to come soon. Okay, there's another way of doing this where I can start by saying that I can do PT equals P times P, where I can raise the matrix to some large power. So I can pre-compute this probability transition matrix, right? And so one way of doing this is in a for loop. I can do this. I can do this multiplication t minus 1 times. You can also do something a little bit smarter by saying I can take this. This will be P2, and then I can say that P4 equals P2 times P2, and then P8 equals P4 times P4, and so I only need to do log T of these matrix multiplies. And so this would be another way of doing it. And so the thing is doing the first one, the power method, this one is going to be a matrix vector multiply, which is going to be faster than a matrix multiply. Okay, so I only need to do t steps of that. Although this one I only need to do log t of these matrix multiplies. Okay, typically the first one is faster, the power method. Especially if your graph is sparse. There'll often be a really big sparse graph with lots of zeros. I can do a matvec on sparse graphs very efficiently, whereas this will become dense very quickly. And so this will be dense matrix multiplies, which will be slow. Okay? Okay, the third way of doing Q star is I'm going to run T random walks, and I'm going to take the average state. Okay, so I can actually put like something that keeps track of a state, like a state machine, and say I'm in state A, I'm in state B, I'm in state C, and I'm going to run this a bunch of times. And I'm going to run each of them for some large number of steps. And I'm actually probably want to restart this and do this t different times with maybe different initial positions. And then I want to take the average over all of these, and this can be Q star. Okay, and we'll get back to this version. This is kind of this other view of Markov chains, but this will also converge to Q star. Okay, and so then the third version is Q star is going to be the first eigenvector of P. Okay, so you look at the power method, you might have guessed this already, that I'm basically computing the first eigenvector of P. So technically what I want to do is in MATLAB, I can call I of P, and then I want to take the first V1 equals this V matrix. So I want to take the first column of the V matrix here and say Q star is then going to be V1 over some V1. Because the eigenvectors will be given normalized, which means that their L2 norm is going to be 1. I want the L1 norm to be 1, so I need to take the first eigenvector here and then L1 normalize it. So I can divide by the L1 norm or just the sum of the entries here. Okay, they're all going to be positive. Okay, so it's just the first eigenvector of P is also this state. Okay, so now we've come back and we've connected all of this back to eigenvectors. Not the same eigenvector as in spectral clustering. That I created, I took the adjacency, and then I turned that into a Laplacian matrix by doing the diagonal subtracting the adjacency matrix. Okay, so that eigenvector is telling me something different about the matrix, but generally with matrices, the first thing you could think of as what can I do? Can I use eigenanalysis? Graphs are like matrices, and the eigenvectors tell me something interesting. Okay, the other interesting thing about this view of the world is now, so L, what would this be? L2, 2. So L is going to be a diagonal matrix. The second eigenvalue, is going to tell me how fast it converges. How many iterations do I need before I converge? And basically, the smaller this is, the faster the convergence. Okay, so smaller equals faster convergence. Okay, if it's larger, it means they're kind of two things that are trying to both be dominant, and it's not clear which one it is. It could be that they're two almost connected components, which have a small thing going back and forth between them. Remember this transient example where it's slowly leaking out. Allows slow leaks to go both ways, but they're slow leaks. It doesn't know which of the two components is going to be dominant or what the right probability distribution of those is going to be. Maybe it's balanced them inside, but it doesn't know how much is going back and forth, and that part is slow. That would cause it to have a large second eigenvector. And that second component will tell you kind of it tells you how slow is this mixing to the final state. So okay, in the example, in the example we had, so in the example graph we talked about, that was looks something like this, right? This is like A, B, C, D, E, F, G, H. I think it was like this, or pretty close to this. Just to kind of show you that Q star, which you can get by running eigenvector analysis, is non-uniform. Okay, this is A, B, 0.15, 0.15, 0.1. This is C, D, E, F is 0.15, G 0.1, and H is 0.05. Okay, so the nodes which are kind of more central are going to have a higher value. So A, C, D, E, and F are going to have a larger value. The ones which are kind of on the periphery a little bit, B and G, are going to have slightly lower values. And then H, which is the most isolated, is going to have the smallest value of 0.5. Right? So if I did this correctly, you should add up to 1. They're all between 0 and 1, and it's not uniform. It tells you something about the structure of the graph somehow. The more isolated ones, the harder to get to in a random walk, are going to have much smaller values. The ones that are going to be easier to get to in a random walk, they're kind of somewhere in the middle, are going to have higher values. Okay? Kind of the worst case values you can get is if you're going to have kind of a big connected component here, and then this large string here, and the thing way in the end is going to have a very small probability of being there. Because if I'm here, I'm probably going to stay here. If I walk here, I'm going to randomly sometimes walk back this way and get stuck in this component. And very rarely am I going to get here. And if I get here, I'll have to start leaving right away. I might come back, but once I get stuck over here, I'm kind of stuck. Okay, so this is known as a lollipop graph. Right? And so there's this thing about if I don't have this, I just have a single line, then this is called, so just in here is called like the drunkard's so the drunkard's walk example, and that, someone's got drunk or, or is confused and is on the way home, and do they get home or do they wind up someplace else? And they're kind of wandering halfway back and forth. So people have studied these kind of in principle. So cool. Okay, I have 3 minutes left to tell, or 7 minutes left to tell you about this other view, and this is the kind of actual random walk view of these, where I'm at one state at a time. And there's this this interesting story about this was called this Metropolis algorithm. This came about in 1953, and this was kind of the same group of people who helped build the atomic bomb, actually. And they were trying to do simulations on kind of what these explosions would look like, to try and model these explosions in certain ways. and they couldn't write down the probabilities exactly. It was too complicated. So instead they said, well, let's use randomness. And let's kind of just do a bunch of random simulations of this and see what happens. And this started like 10 years prior to this, right? The atomic bomb was like dropped in 45, right? So it took them a while to build this. And so this was not early on accepted that you could do random things and they would kind of eventually tell you the right distribution of the outcomes. And so it took until 53 that they kind of formalized this idea of this metropolis algorithm. And this was kind of the start of this stuff with Markov chains. Rosenbluth and Rosenbluth were married, and Teller were married, and metropolis had the first initial that was the lowest in the alphabet. And so he gets the algorithm is named after him. So I've heard that's not the right distribution of effort, but I've heard different accounts of whether the Rosenbluths or the Tellers should get the most credit. So then this kind of was used in physics for a while. Around 1970, Hastings kind of generalized this a bit more, and then in the late 80s, this became kind of turned into this idea called Gibbs sampling, which is the basis of computational Bayesian statistics. Okay, Bayesian statistics will set up these probability distributions and say, given your prior and this data, this is what we know about the complex world, but we don't know how to calculate it. Okay, and so then they said we can use these Markov chains to calculate this sort of stuff by running random walks. And this is how a lot of computational Bayesian statistics works, is that they just run random walks to try and understand these complex probability distributions so that they've set up. Okay, and so why this is interesting and different from what this graph view of the things is that V now, the state space, is usually not finite. I don't have edges between things, but I've got a continuous state space of a probability distribution, and I have I need to set up some relation between them. Okay, and so because I'm running out of time, I'm going to kind of jump to the algorithm and try and explain what's going on here. So I can still describe this on a finite state space, and this might be a little bit easier to think about. But I can initialize by exactly one state. So this is just the initialization of my state. I have exactly one state, but this could be effectively an infinite dimensional vector of possible states. Okay? And so then what I'm going to do is I'm going to take my state, it could be a continuous object, and I'm going to generate something that's nearby. So I'm guess nearby state U, right? And so this could be like a kernel, like a Gaussian kernel defined over. If I'm in 2 dimensions, it can be defined over the plane, right? So I'm more likely to jump to something nearby. This tends to kind of make sense, although it doesn't matter so much what K is for this to work. Okay, and so now all I have access to this probability distribution, or this could be used in physics as well, is some weight function. And in probability, think of this as the likelihood function. If you know what a likelihood function is, it's basically this is basically a probability divided or multiplied by some unknown kind of value, which if I divide through by, it's multiplied by something, some normalization factor, which I don't know what it is, and if I divide through the likelihood by the normalization factor, it'll be a probability and integrate to 1, but the likelihood itself might not integrate to 1. Okay? So I just have some weight. I can evaluate the likelihood of a certain state, or in physics, I can calculate the energy of the state. Okay? So it can also be something like the energy here. Okay, and I'd like to be at a lower, or maybe this is e to the negative energy. So I'd like to be in a lower energy state. So the higher energy, I don't want to be in there. So this will bias me towards a low energy state. So that e to the negative energy would be, if it's high, that'd be a low energy state. Okay, and so I look at the proposed state u, and if the weight is greater, then I'm going to make the step. Okay, so if I'm at state v, I move to state u. If the weight is greater, that means it's a better state. I'm going to move there in the random walk. But if the weight would go down, say it's a higher energy configuration, I still might make the step, but with only probability proportional onto these weights. Okay? And then, so I could be the next state is the same as the state I was in before. And then I wait until this process converges, and that's kind of a dark art. Okay. So what's going on here is that there's some unknown weight distribution. This will converge to, this converges to this weight distribution. It's kind of the magical thing that happens here. Based on like looking at the properties of like the delicate balance, you can guarantee that this will eventually converge to the, look at all the distribution of the states I wound up at, this will converge to this weight distribution here. And it will allow me to essentially normalize this distribution. I can only evaluate the energy at any point, and this will tell me in the limit, I'm going to kind of, the distribution will mimic the kind of the, I'm more likely to be at these low energy states. Usually they have this Boltzmann sort of conversion up here. Okay, or this is used to kind of understand the distribution of a distribution where I can only write it down, and in order to get actual states that I can like actually work with data, I run the simulation. Okay, and so how long do you run this? What do? You typically run it for a burn-in period of like 1,000 steps, and then I average everything the next 5,000 states. The first steps may have bias based on the initial condition, but after 1,000 steps, I'm in a random space, and then if I walk around, it does a pretty good job. In theory, you're supposed to kind of reset every 1,000 steps and take one state every 1,000 steps, but usually people don't do that because it's you're throwing a lot of information away. So in practice, do a burn-in of 1,000. Usually it's 1,000 for whatever reason, and then you do like the next 5 or 10,000 as your distribution. Okay, I'll stop there. We'll see how to use this in PageRank, a very influential algorithm, on Wednesday.